Good morning. Welcome back from your weekend. So we have seen what is logistic regression in the previous classes, and we have tried deriving logistic regression logistic regression means it's binary classification. We have softmax regression or K-class logistic regression. We have derived the gradient expressions, right? And we have told that this is a generalized linear model. Okay, and I hope you know the reason for calling this generalized linear model. Okay, so if you actually, though you have a softmax or sigmoid at the end, you are making use of a linear model to discriminate. Okay, at p is equals to half, you actually found that your linear equation w naught plus w1 x is 0, right? That's what you have seen when this is 0.5. It means that it is just the boundary between class 1 and class 2, and at that location your linear model is just like a hyperplane. So you are calling this as generalized linear model. Okay, so there was a question in last class. Suppose if my data is distributed like this, okay, at 4 corners, where and I'm trying to do 4-class classification. Okay, assuming that you are doing 4-class classification and your data is distributed in this way. Now the question is, can my logistic regression solve this problem? Can you tell me whether it will solve or not? Ideally, what kind of decision boundary you expect? Maybe this kind of decision boundary should work, right? This is the ideal decision boundary, right? Which you need to solve this kind of data distributions or this kind of problem. Now the question is, can my logistic regression give this kind of decision boundary? Okay, to answer this, you go and simulate and see. Okay, so once you simulate, then we'll try to draw the theoretical interpretation for it. Okay, so this is one takeaway question from last class, from last tutorial. And there was one more thing, and this is pending from my side. I'll try to do it. Maybe by tomorrow I'll try to do this. Okay, where we need to, like, I simply extended from binary and we try to prove the gradient expressions, right? In case of K-class classification, that is your softmax. When you use softmax at the end. So instead of extending, can we directly derive that? Okay, so that I'll try to do it and maybe post it by tomorrow. Okay, fine. So there were some questions on Piazza asking about bias variance diagrams, and there were some questions about K-class classification. Why am I using this notation? Why did I have a transpose here? See here, my aim is to, this was the question was, somewhere in my K-class classification using least squares, I wrote this expression. Okay, where the element or the kth element in my vector is equals to something like this. Okay, so the question is why there is a transpose. See, you can use any notation. Your aim is to do linear, like the multiplication with your W vector and just take the sum. It is just a linear sum. You can see based on your dimensions of xk and wk. So if your xk and wk are like this, then you can use xk into wk. And if your wk is, if your xk is a vertical, like if this is your wk transpose, and this can become your xk, and this can become your xk. And see, it depends on the dimension of your xk and wk. Okay, so you can denote with xk into wk or wk transpose into xk. The aim is to do linear sum. That's it. Okay, so this was the question. And one more question was, in my one hot encoded vector, I'm saying that I have a vector and which is summing up to 1, right? Just a minute, I'll just check the question. So this, see, when I explained least squares, I told that one hot encoder is having a vector and those are probabilities and they sum up to 1. But in my least squares, I am not imposing the condition. And his question was, in this case, do we need a separate function to find probabilities? That's what we are doing in our logistic regression, right? In our least squares, we don't have a function to transform to probabilities. And in your logistic regression, you have a function. Okay, I think I have answered the questions. And the one more question was to explain bias variance trade-off diagrams. So I'll just quickly explain those. See, in your bias variance trade-off, basically what do? You take your test error and you call that as generalized error and you write, like decompose that error into 3 terms: bias, variance and irreducible noise, right? So bias refers to your training error that you can recall, right? It refers to your training error, and variance refers to basically if you have multiple models trained on multiple subsets and what is the variance between all of those, okay? And if they are actually, see, each model you have, HD1 to HD2, all of these are different models trained on different subsets. Okay, so if there is variance between all of these models, it means that each model is over specializing on that particular data set. Okay, so that's what we have seen in our bias variance trade-off. So if you see, bias is like a training error. Okay, so what happens to your training error when your model complexity increases? When you start to increase your model complexity or the number of parameters, it means that you will actually try to fit your training data so well. You have observed in this scenario, right, where you have some data points distributed like this, and you will actually try to fit a function which will have training error almost 0. And you are making your model more complex. So as you make your model more complex, you will try to fit the training data so well, and you will actually over specialize on the training data. So that makes your training error 0, right? Training error 0 means that bias will become 0 or bias will tend to a lower value. So that is happening in this figure. Like if you, as you are increasing model complexity, your bias is decreasing. Yes, so bias is decreasing, and as you, bias is nothing but a training error. So training error will decrease, right? And what happens to your variance? Variance is basically increasing because variance will increase when you overfit your data, right? Because if you see, variance will increase when my HD1 model is specializing on D1, my HD2 model is specializing on D2. Like this, if they have, like all of the individual models are over specializing on individual data set, then if you compute the variance between all of these values. So what is your variance? Can you help me recall? It is something like this, where you take your mean model and where you take your HDK and square and sum over k is equals to 1. Something like this you will have, no? Where you will find the variance among your predictions, your individual predictions. So the variance will be high whenever your model over specializes on that particular data. So then, as your model complexity increases, you will start to overfit and then your variance increases. Okay, then what happens to your test error? This is like your test error. Okay, so test error, as your model complexity, when your model complexity is too small, your test error is high because you may not fit well. Okay, you may not actually fit the data well. As your model complexity increases, again your test error is going up. Okay, so this is your underfitting scenario and this is your overfitting scenario, right? Okay, so what do you need? You need optimal model complexity. Okay, optimal model complexity which balances between your bias and variance. Okay, if bias is too low and variance is too high, maybe overfitting, and if your bias is high and the variance is low, maybe underfitting. So you need to balance between your bias and variance, and you need to select the optimal model complexity which will minimize the test error. Now, you should not concentrate on the train error, right? Test error is important. That will generalize, that will actually decide the generalization performance of your model. Okay, so this is fine, this figure is fine. Okay. Okay, so now coming to this figure, it is basically, see, your blue, this red color one is your ground truth. Okay, the red color circle is your ground truth and the blue color ones are predicted by each HD1, HD, okay, each individual model. Before we set up our bias variance trade-off itself, I have told you that we are training multiple models, right, with different subsets. So these are the predictions by multiple models. So when we look at this figure, so all of these predicted points are closer to your ground truth. So it means that the training error is less because ground truth is red color one and blue color one is predicted for the training data set. So in this case, training error is less. Okay. So, but the cluster, if you see, they are still closer to each other. Then you can say that the variance is also low. And now coming to this case, see here I actually have some bias. My predicted value, the blue color points are slightly far away from your red color, the ground truth one, but they are still closer. They are just within that circle. Okay, so in this case, he is still considering the bias as low. Okay, maybe a particular threshold, the bias is low. And if you observe these blue color points, see each point corresponds to each HD1, HD2, right? So if you just see the variance among this, variance is high. So this is high variance. And now in this case, if you see, this is my ground truth and this is the predicted one. So they are far away, so bias is high, but they are clustered together. Okay, the variance among those predictions is less. So the variance is less. And here I have variance high and the bias high because they are far away from my ground truth, and the spread, if you observe, the variance is high. Okay, hope I answered the student's question. Okay, it's fine. So now, till now what we have seen, like we started setting up our least squares, then bias variance, and then logistic regression, right? So all of these approaches, like at least the two kinds of classifiers that we saw, can I call them as discriminative approaches, where given, see, if I have to do classification, there are two approaches. One is your discriminative approach and one is your generative approach. Okay, so in discriminative approach, given the data points, basically, suppose if you have two classes given to you, a binary classification data set, maybe a class 1, class 2 data sets are given to you, then in discriminative approach, we will only focus on learning this hyperplane or the decision boundary. Only the boundary we'll try to learn. Okay, so if you see, if you go back to our logistic regression case, I'm learning a hyperplane or a decision boundary like this, then I'm applying a sigmoid on top of that. Right? So I'm focusing mostly on learning the hyperplane. That's it in the discriminative approach. So till now whatever we have seen, both of them are like discriminative approaches only. Right? So in your generative approach, what do we do? Given class 1 and class 2 data points, we will actually see how these class 1 data points are generated and how class 2 data points are generated. When I say generated, definitely we need to deal with distribution functions. Okay, so now in generative approach, what I'll do, I'll try to estimate or model the distribution function for my class 1 and distribution function for my class 2. Okay, then using the distribution functions also, see, if I know the distribution function which gave out my class 1 samples and which gave out my class 2 samples, if I have access to my distribution function, I can make use of those distribution functions and solve my classification problem. Do you agree with that? How can I make use of the distribution functions and then use that for my classification work? I will not focus on learning this decision boundary anymore. See, if I learn these two, automatically I may learn decision boundary. But yeah, but I'm not focusing on, I'm not parameterizing the boundary and learning the parameters. Okay, so in your logistic regression, I parameterized this and I learned this, right? These parameters, W naught. Okay. So I parameterized this boundary and I started learning the parameters for the boundary. But in generative approach, I will not learn the boundary directly. Instead, I will learn the probability density function or distribution function for both the classes separately and then make use of those probability functions to do the classification task. Yeah, tell me. That's based on the assumptions. In the first class I have told you, right, when you don't know the distribution, when you are just given with some data points, okay, you don't know anything, somebody gave you some data points. The first assumption was they are coming from a Gaussian, right? So that assumption will make. If you have some prior information that, okay, these data points are coming from some exponential or Laplacian, some distributions, then you can start with your prior information. But when the prior is not given or the prior information or when you don't know anything, we have to assume. Okay, so that's why we have seen why Gaussian, right? Fine. Fine now. So I will try to learn the distribution functions for my given data set. So when I am learning, I assume that they follow Gaussian. Okay. So if you ask me why are you assuming, you know the reasons. And I mean, you may ask me, is it always correct if I assume Gaussian? But it may not be. If the real world data is following some other distribution, you may not optimally fitting it, but that's the only thing you can do, right? When you don't have any information, you have to assume. Okay, so now if I learn my distribution function, maybe some C1 and probability of C2. If I have these distributions, so based on using these distribution functions, I will try to do the classification problem. Okay, so let's see one example. So what can you, okay. Okay, assume that you have some two distributions like this, okay, where class 1 is this P of x comma C1 is the class 1's the data points in class 1, and P of x comma C2 is the distribution of class 2. Okay, so if you have this kind of distributions, okay, so now if you want to do the classification, assume that I am putting my threshold at x hat. Okay, So assuming that I am actually putting this x hat and I am dividing the regions into R1 and R2. So R1 belongs to class 1 and R2 belongs to class 2. Okay, so if I am dividing my entire, see this is just a 1D dimension or a univariate dimension, and I am dividing my axis into class 1 and class 2, but the actual distributions are like this. Okay, so now if I use x hat to do class 1 and class 2 separation, if I use x hat, then what we have to, like given this distributions, we have to find out the probability of mistake. Okay, so if I given this kind of distributions are like this, okay, and you are using x hat to do the separation. Okay, so in that case we have to find out probability of mistake. So in the probability of mistake, how will we do? Suppose in region 2, you are in region 2, but there is some probability for your, okay, so maybe assume that a data point, some data point is coming from R2, okay, but it is maybe still coming from your, this distribution, C1. Okay, because my probability of x comma C1 is also there in my R2. Okay, so then these data points actually will see, if my data point is in this region, no, in this region, and it may come from my class 1, but because of my boundary it may fall into my class 2, right? Because of my x hat, I am actually saying that, I am actually predicting that my data point belongs to class 2 based on my boundary, but it is coming from my class 1, okay, because of this distribution. So in that case, my probability of mistake will be R2 P of x comma C1 into dx. Do you agree with this? My x is following this distribution, but because of my x hat, it is falling into region 2. Okay, so in the same way, you can have one more term for your probability of mistake, that is your data point is actually coming from this distribution, but because of your x hat, it is falling into region 1. Okay. Now, this things actually, see, integration is nothing but finding out the area under that curve. So can we actually find out these, this entire quantity using the areas? So I'll try to give some notations to this. So for my first term, maybe this is A, B, C and D. Okay. So for my first term, when I am finding out the probability of mistake, so the first term will be A. Do you agree with that? It's just A. First term, first integration is A, because I am just giving this area, denoting this area as A. So my second integration is where x is in region 2, but it is coming from my P of x comma C2. Then my integration will become B, C plus D, right? B plus D, C plus D. Okay. Fine. So now, is this fine? This is my probability of mistake if I take my x hat as the boundary or the separating line, right? So if I am taking x hat as the separating line, and if my actual distributions of my P of x comma C1 and P of x comma C2 are like this, then you may make some errors. Okay, if you use that, then the error I am quantifying using these integrations. Fine. So now move, yes. What is? X naught I'll tell you, but as of now, like, you concentrate only on x hat. If I am taking x hat as the boundary, then this is the probability of mistake Did you get till there? Okay. So now you change your x hat to x naught. Okay. Change your the boundary from x hat to x naught. Okay. So see, the boundary I can fix it, right? I'm just experimenting with two boundaries now. Okay, in the first case I have taken x hat and found out my probability of mistake. Now I am moving my x hat from x hat to x naught. So if this is your separating hyperplane, then this becomes, okay, so this becomes your R1 and this becomes your R2 with your x naught as the separating hyperplane. So now, can you write probability of mistake for this case? Probability of mistake with x naught as the separating hyperplane. So what do you have to do? X is coming from R2, but it is still following your distribution. This becomes your one term in your probability of mistake. The other term is x is coming from R1 but it is still following the distribution of, the opposite one. Okay, so these two terms basically will give you the probability of mistake. Okay, so now can you tell me, we have given the notations, no? This as A, B, this is C and D. Okay. Now can you tell me the probability of mistake in this case where I am using x naught as the separating hyperplane? What happens to my probability of mistake? What happens to this first term? A plus C. The first term is A plus C because my R2, this is my P of x comma C1 and this is my R2. So this entire region will be the probability of mistake using this first term. Yes, A plus C, right? And the second term is what? Concentrate only on x naught. Okay, so using my x naught, if I have to compute this where my x is coming from R1 but it is following the distribution of P of x comma C2, then in that case you need to consider only this, right? Only this. Then this becomes A plus C plus D. Yes. So in the previous case when I used my x hat, my probability of mistake is A plus C plus D, and when I am using x naught, probability of mistake is A plus C plus D. Okay, so ideally which one is better? X naught is better, right? X naught is better. So in our classification using this distribution modeling where I will make use of the distribution functions in class 1 and class 2 and solve my classification problem. Your aim is to minimize probability of mistake. Choose your boundary or choose your separating hyperplane such that your probability of mistake is minimized. Okay, so in the previous case what I was doing, I am minimizing the mean squared error, right? Mean squared error. But now I'm putting, I'm actually formulating my entire classification problem as a distribution estimation. Like I'm trying to estimate or learn the distribution functions. So here I am actually formulating it as minimizing probability of mistake. Okay, is this fine? So now you have to learn your classifier. See this. Okay, you have to basically choose your x naught such that your probability of mistake is minimized. Okay. So this will be minimized with a particular condition. So I will tell you what is that. So if your probability of x comma c1 is greater than probability of x comma c2, just assign x to r1 or the class 1. Okay. So not r1, just assign it to class 1. And if your probability of x comma c2 is greater than probability of x comma c1, then assign it to x c2, and if they both are equal, then that means that is on the boundary, right? If both are equal, it means that that is your boundary. Okay, so if you actually have this kind of condition where probability of x comma c1 is greater than probability of x comma c2, then assign that data point to c1, and if it is c2 is greater, then assign it to c2. Okay, so here if you see that same figure, so if you see, just focus only on my x naught as the separating one. If you see in this region, in my this region, no, till x naught, my probability of x comma c1 is greater than probability of x comma c2. Yes. Okay, in my R2, my probability of x comma c2 is greater than probability of x comma c1. Yes. So for this particular case, my x naught is the optimal hyperplane. No, can you actually reduce your error further than your a plus c plus d? That is your probability of mistake with my x naught. Can you actually try moving your x naught to this side or this side, and can you reduce your probability of mistake further? This is the best, no, for this particular distribution, x naught is the best one, and which will give you the minimum probability of mistake. Okay, and at that point where your probability of mistake is minimum, if you observe, it is following these conditions. Probability of x comma c1 is greater than probability of x2 for class 1, and probability of x comma c2 is probability of x comma c1 in your c2. Okay, so this is called your Bayes classifier, where you will try to estimate the distribution functions. Like suppose if you have some class 1 and class 2 data points, you will estimate the distribution function of this and estimate distribution function of this. Okay, and using these distribution functions, you will once you estimate this distribution functions, when the new test data point comes, okay, the test data training is nothing but fitting these. Okay, fitting this is nothing but your training. Okay, so once you complete your training, meaning that once you fit your distribution functions, in future when the new test data point comes, you just substitute your test data point in C1 and probability of x test of C2, then whichever is maximum, just assign x test to that class. Okay, so this is your basic formulation of your Bayes classifier. Okay, and in Bayes classifier you are trying to minimize probability of mistake. Okay, fine. So now if you see, suppose you have class 1 and class 2, which is like diabetes positive and maybe diabetes negative. Okay, you are trying to solve a medical problem where you have some data points with you with some dimension d, and then you have the label as diabetes positive and diabetes negatives, and class 1 and class 2 you have. Okay, so if you have to estimate this probability of C1, can you write this as in, can you use Bayes theorem and expand this? So this can be written as probability of C1 comma x. This becomes probability of C1 sorry, what can I write? This can be written like this, no? Okay, just using the Bayes theorem, you can expand this. Okay, so now it actually, okay, suppose, is this fine? Just a simple Bayes theorem I am applying, and I am trying to expand my joint probability into conditional probability. Okay, so if this is the case, and if you have x as like some data point, meaning this x is the feature vector of a particular person, okay, and you have to predict whether that particular person has diabetes or not, C1 or C2. Okay, so this you have to predict, right? So if you directly want to learn this joint probability density function, it becomes very hard, like, yeah, it becomes hard, right? Yeah, it becomes hard. So instead of that, what we will use? We will directly use probability of C1x. See, if you want to solve your classification problem, you have to basically apply this rule, right? Based on this joint PDFs, whichever is maximum, you will assign to class 1 or class 2, right? So this is equivalent to doing or else, just a minute, we will just substitute probability of x comma C1 into probability of C1 greater than probability of x given C1, C2, probability of C2. So now, what is this probability of C1 and probability of C2? Distributions, but they are like priors, right? They are called priors. It means you are solving the problem of diabetes positive or negative for a particular person. So what is this P of C1? It is the probability of diabetes, having diabetes. P of C1 is not taking that particular person's information. Okay, so P of C1 is without like knowing anything about your X, without knowing anything about that person, you are predicting what is the probability of diabetes. Do you understand what is P of C1? See, C1 is positive class and C2 is negative class, okay, negative diabetes. And P of C1, it is telling you the probability of having diabetes, but it is not considering anything about your X, that particular person's X. So then how can you get the information of P of C1? It is in general irrespective of my X, you have to tell me what is the probability of that particular class, right? Meaning that you need to know the infinite number of data points, or maybe all of your Indian population, if you want to model it for India, like you have to know the entire population's data, whether they have diabetes or like positive or negative. Then using that you have to get your P of C1, right? Because it is not depending on the X or the data point, a specific data point. It is basically modeling whether the diabetes positive or negative. Okay, so this depends on population, like the infinite number of samples. This is called your prior. Okay, see, maybe if you go to a doctor without knowing anything about that X, he should have some idea whether that is positive class or negative class. Okay, so that is called your prior information. So now, do you understand it is very difficult to get the prior information? Just for this case, if you see diabetes positive and a negative case, how will you get the prior information? Maybe if you have like 1000 2000 samples, you may see whether how many classes are positive and how many points are negative, and then you may get some estimate for your prior. But it is still depending on that 2000 samples. Okay. And even if you take like too many samples, it's very difficult to get, right? So given a particular problem, without observing that data set, if you have to comment on the classes, you need to know the prior information, right? Do you agree with me? So the prior information, it's very hard to get. So in this Bayes classification, we assume that this P of C1 is uniform. You don't know, like when you don't have any information, you can assume it to be uniform. If you assume uniform, then there is no problem, right? There is no bias. You are not giving class 1 more priority or class 2 more priority. All the classes you are assuming to be uniformly distributed. Okay. So when you don't know prior, you are just assuming that P of C1 is equals to P of C2 when X is not known. So in that case, you can just cancel out these two. These two you can cancel out. Yes, these two you can cancel out. So then this is the joint, like when we started, I told you that to minimize probability of mistake, use this condition to do your classification. Now this condition, the joint PDF, I am replacing with this term. This is called your likelihood. Okay, this is called your likelihood. And this is your prior. And I am assuming my prior to be uniform, and I am cancelling out those two terms, and I am only learning this conditional PDFs. Okay, I think this is what you have done in your Bayes. You don't do joint PDF estimation, no, in your Bayes classifier. You do only this likelihood estimate or this conditional PDF. Yes. So now, if you have this C1 and C2, you don't do joint, you do this. Okay, and we try to estimate this, estimate these PDFs, conditional PDFs, and make use of these PDFs to classify your unseen or test data points. Okay, and when I say you estimate this conditional PDFs, again you have to assume they follow a Gaussian, and then you try to estimate. If you have some information, the prior information that you have, if you have some prior information saying that okay, this real world data is not following a Gaussian, it is following a exponential, then you have to fit exponentials, right? And now if you know the prior information, meaning that the P of C1 and P of C2, without observing your X data points, you have some information about your classes. Assume that you have some information. Then you have to integrate that also. So instead of P of X comma C1, in that case you will introduce P of C2. Okay. So whenever you assume your this P of C1 and P of C2, these are priors to be uniform, you ignore your priors. Okay, so then that comes under your MLE estimate or maximum likelihood estimate. Okay, whenever you consider priors, that P of C1 and P of C2, you have some knowledge about P of C1 and P of C2, that becomes your map estimate. Have you heard of map estimation, MLE estimation? Yes, you have seen that already. In which course you have seen? Oh, right now it's going on, the map estimate and MLE estimate? Previous semester. Okay then. So now you can relate, no? You can have a prior information about P of C1, P of C2, then that becomes your map estimate. Whenever you ignore P of C1 and P of C2 and make it uniform, it becomes your maximum likelihood estimation. Okay, so in Bayes classifier, I generally ignore this and we will try to fit these. Okay, so we'll see the derivation for Bayes classifier in next class. Hope you got the motivation for Bayes classifier. Basically, I'm trying to learn two distributions and my aim is to apply that rule, and that rule is coming to me by minimizing my probability of mistake. Okay, fine. Just